Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video on a series for reviewing how to solve nonlinear inequalities. The previous video in this series was focused on solving quadratic inequalities. We only needed one example to do that. In this video, we're going to focus on solving rational inequalities. And the tactic we're going to use is very similar to what I used for solving quadratic inequalities. I'll showcase the two methods here. The two methods we did last time were building a sign chart and then graphing. Let's go ahead and, again, just showcase both methods. We'll do the sign chart first, mainly because that's how most people teach this topic, even though it does not need to be taught that way. So how would you use a sign chart? Well, the first thing you do when you solve an inequality is move everything to one side. That's basically what we did with the quadratic inequality in the last video. So I'm going to go ahead and grab this fraction and move it over to the other side of the inequality. And I'll do that down here. Now, before I continue, I just want to let you know, you could have moved everything to the left-hand side. It doesn't really matter. This is an arbitrary decision that I decided to move everything to the right-hand side. The second thing you'll need to do is combine these fractions up. Adding two rational expressions is a prerequisite for this course, which is either college algebra or pre-calculus. So we know we would need an LCD. And then we know we're going to have to make equivalent fractions with the same denominators. So all I did here was multiply each fraction by the necessary factors so that we have common denominators. Also notice, the first fraction I multiplied by x plus 3 over x plus 3. Basically, I multiplied by the number 1. That's what x plus 3 over x plus 3 is. So I'm not really changing the value of that fraction, just the look of it. I did the same thing for the second fraction. I multiplied the numerator and denominator by x minus 2. Again, essentially I'm multiplying by 1. Now at this point, because they have the same denominators, we can glue these two fractions together. Couple things I want to note. 1, I see a lot of people do this. When they get to this point, they start canceling. You would be undoing your work if you started canceling right now. You don't want to cancel. What you want to do is distribute things out in that numerator. The other thing I need to mention here is my liberal use of parentheses. You need to use parentheses like I'm using them here. If you did not use parentheses, let's pretend you just wrote that multiplication in this numerator like that. Really what you're saying is you have x times minus, and x plus 3. And that is not the same as this statement right here. This statement means you're going to distribute through, and this is the proper statement. So just to let you know, you have to use parentheses liberally. I should not have to tell you why. It is true that you do have to use that because you're multiplying that entire numerator by x plus 3, not just the -1. So make sure you use parentheses. Now, like I just said a moment ago, go ahead and distribute out the numerator. Do not distribute out that denominator. All right, so let's talk a little bit about this. You should know how to distribute, so I'm not going to have to review that, but notice that I kept these parentheses on this last bit because we're subtracting everything in there. So I just want to wait to distribute that subtraction until after I've done the distribution, which I've finally done. So let's go ahead and distribute that subtraction through. You get down to this, and then you just combine like terms in the numerator. Now, before I continue any further, I want to make sure that you understand I did not multiply out the denominator because having denominators factored is very advantageous. You want to leave those factored. However, I did distribute out this numerator here because, well, we have two different terms full of messiness. Distributing things through allows us to combine like terms and then simplify down to 2x plus 1 in the numerator. So it is very advantageous to distribute through in the numerator. Now we get to this point right here, and we need to figure out when is this fraction greater than 0. So I'm going to go ahead and make a sign chart. Now remember, that's the whole point of this, is to make a sign chart. So I'm going to make a sign chart here, and the sign chart will include where I have division by 0, which, by the way, I tell you right now, x cannot be 2, nor can x be a negative 3. So I'll go ahead and mark those points on my number line here. And then you're also going to mark where your numerator turns into 0. And that occurs at x equals negative 1/2, which is probably, let's just pretend, right around here. So notice my number line has been broken into 1, 2, 3, 4 sections. Each of those sections I'm going to test for whether or not my fraction is positive or negative. In other words, I want my fraction to be positive, so I'm going to test those intervals to see if it is actually positive in each of those intervals. For any value of x less than negative 3, so let's go ahead and just try x equals negative 4, because, well, that's less than negative 3. Our fraction would become negative 8 plus 1 over, let's see, we're plugging in negative 4, so over a negative 4 minus 2, which is a negative 6, and a negative 4 plus 3, which is a negative 1. Now taking a look at the mathematics here, negative 8 plus 1 is negative 7, divided by a positive 6. That fraction is going to be negative when I choose any x value less than negative 3. Well, we don't want our fraction to be negative, we want it to be positive. So this interval from negative infinity up to negative 3 is not going to work. Now, if you watch any of my other videos, when I test regions, on the edges here, I tend to plug in super ridiculous numbers. Like in this case, I would not plug in normally a negative 4, I'd plug in a negative trillion. Why do I do that? Because think about this fraction right here. If you were to plug a negative trillion into the numerator, well, it's obviously negative. I don't have to do the mathematics to know the numerator is negative. And if I were to plug in a negative trillion into that denominator, it would be a negative number times a negative number, which is positive. Again, I don't really need to do the mathematics, I just need to know what the signs are, and negative over positive is going to be negative, which is not what I wanted, so therefore I don't include that region in my solution set. Now let's pick a number between negative 3 and negative 1/2. This, I do have to pick a nice clean number, so let's pick like a negative 1. I'll zoom out a little bit to make my math a little cleaner. X is equal to a negative 1, and if you plug a negative 1 into this fraction, you will get the following. That numerator is going to be negative, the denominator is going to be negative, and negative over negative is positive. That is exactly what we want our fraction to be, is positive. So there we go. We know that in that region between negative 3 and negative 1/2, our fraction will be positive. It will satisfy this inequality. Something else actually just occurred to me as we go through this. Notice this is a strict inequality. That is, we're not concerned with our fraction ever equaling 0. So, because our fraction will equal 0 at negative 1/2, I'm going to put an open circle at x equals negative 1/2 there instead of a closed circle. Again, that's just because I don't need x to be, our fraction to be 0. I want it to be greater than 0. Anyhow, let's go ahead and test any number between negative 1/2 and positive 2. Obviously, a very easy choice would be x equals 0. Going to the fraction, if you were to plug 0 in, you would get 1 over negative 6. That's a negative number, and that's not what we want. We want our fraction to be positive, so I'll throw out that region. And finally, pick any number greater than 2. And in this case, I'll go ahead and showcase what I was mentioning a moment ago. I'm going to plug in a trillion. Well, if you plug in a trillion, then you get a super positive number in the numerator of this fraction, and in the denominator, you get the product of two positive numbers. Well, obviously that fraction is going to be positive, which is exactly what we wanted, so we get to include that region in our solution set. Thus, the solution to the original inequality is going to be the union of these two intervals. And this side goes on forever. Writing that in interval notation from low to high, we start at -3, climb all the way up to -1/2. We will not include the -3, and we will not include the -1/2. We will skip over the middle region, so we union to that, a region starting at 2 and going off to infinity. You cannot include 2, and obviously infinity is a concept, you'll never include it, so there we go. That is the solution set to the original inequality. The second method to doing this, which is via graphing, might be a little high level for you right now, but I'm going to do it anyway. This is something that you'll generally do later on in a college algebra or a pre-calculus course, but it's always nice to see or be exposed to this idea from the get-go. And a lot of students hate graphing, but the reality is all the work you did for the sign chart method is going to be mimicked here. You're going to do all the same stuff in the first step, the second step, the third step. You can't avoid doing all this work. Fourth step, fifth step, even that sixth step. All that stuff you're copying. Basically, we get down to this point right here. You've copied all that and you're asking yourself, when is 2x plus 1 over x minus 2 times x plus 3, when is that graph above the height of 0? In other words, when is that graph above the x-axis? Now, I just want to show you how fast this can be done. I quickly drew out x and y axes. I know I'll have a vertical asymptote at x equals 2. If you don't know what a vertical asymptote is, it's because you're likely it's been a while since you've been in algebra and you're starting a college algebra class. You should know what a vertical asymptote is, but if it's early in a college algebra course, then the likelihood is you're going to review that later on. I'll also draw a vertical asymptote at x equals -3 because that also causes division by 0. And then at this point, I'm just going to plot our x-intercept. The x-intercept occurs when our numerator is 0, which is a -1/2. So somewhere around there. Now, if you have done any type of graphing of rational functions in your intermediate algebra course prior to college algebra, you know what's going to happen next. The best thing to do is figure out what the y-intercept is. Y-intercepts occur when x is 0. So if you let x equal 0 in that fraction, you will get that y is equal to 1 over a -6. So this tells me my y-intercept is right here. We only have one x-intercept and one y-intercept. So my graph is going to look like this. It's a function, so it passes the vertical line test, so it's not going to do something silly like this. It can't. It has to pass the vertical line test. Also, as we move forward through this course and review your graphs of rational functions, you will then recall, oh, the multiplicity of that x-intercept is 1, so it just goes through that like a line. The multiplicity of this vertical asymptote is odd, so it does this on the other side, the opposite behaviors on both sides, and the multiplicity of this vertical asymptote is odd as well, and so it has the opposite behavior on that side of the vertical asymptote. Note that there are no other x-intercepts, so whatever happens right here, whether it goes down or up or whatever, it will not cross the x-axis anywhere. So it will always be above the x-axis. Now remember, we're asking, when is this fraction above the x-axis? Well, I can highlight that right now. All of those x values, you could see the blue curve is above the x-axis. On the left-hand side here, this blue curve can't go above the x-axis because there's no other x-intercepts, so it's going to stay below the x-axis. And I'm not really worried right now as to the behavior at the edges. All I'm worried about is, when will it be above the x-axis? And you can see that occurs between -3 and this point right here. which is a -1/2. So looking at that, I could tell that our solutions will be x values between -3 and -1/2, and then hop over this area where our curve is below the x-axis and start back up at x equals 2, not including it, and going on to infinity. Notice these two solutions are identical. This idea of using the graph of a rational function to solve a rational inequality is very, very powerful. However, it's completely forgivable if you're just starting in college algebra and you have not reviewed rational functions. In our college algebra course at Cosumnes River College, we do not go into this level of detail about rational graphs until we're about maybe a month into the course. So this is totally okay if you look at method 2 and say, man, I don't get that. It's fine, because what's going to happen is we'll fill in those details later on. For now, you could totally use the sign chart method. If on the other hand, you're in pre-calculus, you should know how to graph a rational function, and graphing the rational function is actually a much better way of solving this rational inequality. It doesn't take long for me to scratch out quickly a graph of a rational function. And you as a pre-calculus student should also be pretty quick at graphing out a rational function. So solving that rational inequality should be okay. But I don't force your hand, you could do either or. Now, just like we did with solving quadratic inequalities, we only have one example here, and that's because once you see one example, you've seen them all, and this is supposed to be a review. In the next video, we're going to solve absolute value inequalities. I hope to see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.